Industrial tanks at manufacturing hubs are active, complex nodes in a production line and serious liability vectors. Inside these vessels, specific hazards accumulate quietly over time. Water systems breed biological growth in sediment. Chemical process vessels build up highly reactive residues. Petroleum tanks trap volatile, flammable vapors. Allowing these materials to persist degrades system performance. It clogs pipes, contaminates product batches, and exposes facility managers to severe legal liabilities. Operations directors face a difficult balancing act. Rigid Australian regulatory standards demand pristine internal conditions, while the financial reality of plant operations dictates that every hour a tank is offline, the facility loses money. Resolving this tension requires a complete shift in decontamination strategy. Modern tank maintenance engineers human risk out of the equation. The industry is moving away from manual entry protocols and adopting highly sophisticated, automated cleaning architectures. Approaching decontamination as an unskilled cleaning task ignores the technical requirements of the asset, leading to higher rates of equipment failure and regulatory breaches. Despite advances in automation, manual entry remains unavoidable for specific assets. Tanks containing intricate internal metal baffles or irregular geometries often prevent machinery from navigating the interior. When human entry is required, Australian standard AS2865 dictates the protocol. This standard classifies confined space entry as a highly governed critical risk operation. This animated diagram illustrates the mandatory continuous atmospheric monitoring required before and during entry. We track 4 specific atmospheric thresholds: oxygen depletion below 19.5%, lower explosive limits above 10%, hydrogen sulfide exceeding 10 parts per million, and carbon monoxide crossing 35 parts per million. Operating within these environments requires a dense compliance infrastructure. That includes documented entry permits, continuous supplied breathing air, and a dedicated standby rescue team stationed directly at the manway. If the atmospheric readings shift, say oxygen levels drop or flammable vapors spike, the rescue team triggers an immediate emergency protocol, physically extracting the worker using a mechanical tripod system. The sheer volume of safety protocols makes manual entry exceptionally expensive. It requires specialized labor, intensive planning, and significant facility downtime to execute legally. Even with perfect adherence to these controls, exposing human personnel to toxic or explosive environments carries significant danger. This method receives a 2-star safety rating. While manual cleaning is occasionally the only mathematical solution for a complex tank, its risk profile and heavy costs make it the method facilities must actively engineer their way out of. The modern alternative relies on automated systems. High-pressure water jetting and continuous foam circulation can strip away encrusted scale and sediment without sending a single person inside the vessel. For food processors and pharmaceutical plants, the most advanced automated architecture is the clean-in-place, or CIP system. This diagram details how a CIP system operates. Rather than disassembling equipment, facilities install fixed pipework and internal rotary jet heads. The process runs on automated timed loops, starting with a concentrated detergent circulation. The system then advances through specific thermal and chemical cycles, like this high-temperature hot water rinse, to mechanically dislodge stubborn product residues. Finally, the system executes acid rinse and sanitization phases. This neutralizes microbial contamination and ensures compliance with AS 4674 food safety standards. The return on investment for CIP infrastructure becomes obvious quickly. Facilities achieve faster batch turnarounds, use fewer chemicals, and reduce personnel risk to zero. But CIP cannot be retrofitted into massive petroleum or bulk chemical storage tanks. For those highly hazardous environments, the solution is track-mounted robotics. These heavy-duty robotic units deploy directly through the tank's manway. Once inside, they navigate the interior floor and walls along predetermined geographic paths. This 3D schematic shows the simultaneous cleaning process. The robot projects a high-pressure water stream to break up sludge, while a trailing vacuum path immediately suctions out the debris. The operator controls everything from outside the tank. This removes human workers from the most dangerous variables of tank cleaning, eliminating exposure to extreme temperatures, flammable vapors, and toxic fumes. While acquiring robotic systems requires significant upfront capital, implementing them instantly upgrades an operation's safety profile to a 5-star rating. This comparative table visualizes the choice operators face. Manual entry is permanently locked at a 2-star rating due to human exposure. In contrast, methods like CIP and robotics secure a 5-star rating by keeping personnel out of the tank entirely. Upgrading to mechanical automation acts as a strategic shield against human liability and prevents the operational paralysis that comes with a major safety incident. Beyond production capabilities, facility managers also carry strict life safety liabilities. Fire suppression water tanks require their own dedicated maintenance strategy. These tanks hold stagnant water for years. Over a standard 5-year cycle, up to 300 millimeters of sediment and biological growth can accumulate unnoticed along the tank floor. This cross-section illustrates exactly why that sediment is dangerous. During an actual fire emergency, the heavy sludge is sucked directly into the intake pump, rapidly crashing the water flow rate to zero and starving the suppression system. To prevent this failure, AS 1851 mandates that fire tanks must be completely drained, manually high-pressure jetted, and inspected for internal corrosion every 5 years. Regardless of the tank type or the cleaning method used, every decontamination process produces the same inevitable byproduct: thousands of liters of contaminated wash water. Managing this waste introduces a strict environmental compliance framework governed by the EPA and local council trade waste agreements. As this flow diagram illustrates, wash water containing petroleum, caustic chemical residues, or heavy metals is strictly prohibited from entering standard stormwater or sewer infrastructure. Proper disposal requires a tightly regulated chain of custody. The waste must be classified on-site, pumped into sealed transport vessels, and processed at approved facilities. You must retain detailed transport manifests and waste classification certificates for every job. Failing to produce this documentation exposes the facility to severe EPA enforcement actions and financial penalties. A decontamination operation is only successfully completed when the physical asset is returned to peak performance and the resulting toxic byproduct is legally neutralized. Managing this effectively requires understanding how 3 core pillars intersect: the mechanical cleaning method, the required frequency, and the governing regulatory standard. This matrix visualizes how different assets demand entirely different operational approaches to remain compliant. Notice the contrast in timelines. A water storage tank operates safely on a 2 to 3 year cleaning cycle. Highly reactive chemical vessels require strict monthly or quarterly interventions to prevent residue adhesion. Each schedule maps directly back to a governing standard, locking fire suppression systems specifically to AS 1851 and food-grade production vessels to AS 4674. Industrial tank decontamination is a technical maintenance protocol that serves as a core component of a facility's compliance strategy. Operations directors secure their facilities by transitioning away from reactive emergency cleanings and implementing continuous, automated maintenance schedules. By proactively engineering human risk out of the equation, operators protect their workforce, secure their compliance audits, and guarantee their facility's future.